Welcome everyone to CTNT 2024. Our first lecture is by Keith Conrad, our very own Keith Conrad, who is going to be talking about using quadratic reciprocity.
Okay, thanks Alvaro. So let's get started here. So what I put up here on the first slide is the basic statement of quadratic reciprocity in terms of the Legendre symbols. So P and Q are odd primes, and we have various formulas for Q on P in terms of P on Q for the main law, and formulas for -1 on P and 2 on P as the so-called supplementary laws. And the way these often, when they're introduced in a number theory course, the way they're often used is to, well, help you determine when one number is a square modulo some prime. And we'll start off doing some stuff like that. But then I want to switch over and use this to do some other things in number theory. That's the general theme of these lectures, is to put quadratic reciprocity to work. So let me just make a quick comment. So the main law, as we have it up there, is usually just stated for two distinct odd primes, although technically, as written, the main law is even true if they're the same prime, just because then the Legendre symbols are 0. But that won't be important for us today. So one of the first things that's done with quadratic reciprocity is to describe when, for an integer a, describe all the primes for which a is a square. So rather than fixing p and asking what are the squares mod p, we fix a and ask when, for which primes p is a square mod p. So as an example, if we wanted to know when is -2 a square mod p, for which primes, we can break this up into a product. Since the Legendre symbol is multiplicative, we can ask when is this equal to 1. Since we have only two terms, the only way this is 1 is when they're both 1 or they're both -1. And so then we can just set those two conditions next to each other. They're both 1, or they're both -1. And in the first case, -1 is a square when p is 1 mod 4. That's the first supplementary law. 2 is a square when p is, well, 1 or 7 mod 8. And so when you put these together, if a prime is 1 mod 4 and 1 or 7 mod 8, that'll only happen when it's 1 mod 8. The other case, if -1 is not a square mod p, p has to be 3 mod 4, and the other option, if 2 is not a square mod p, p has to be 3 or 7. Let's see, does this work if I move this over? It did not work. Let's bring it down here. 3 or 7 mod 8. And those are the same as, together, those only happen when p is 3 mod 8. And so what you see then is that together, -2 is a square mod p if and only if p is 1 or 3 mod 8. So I can never remember this rule. I've burned into my brain the rule for when 2 is a square. I know that's when p is 1 or 7. But for when -2, I can never remember this. If you can, congratulations, you're using your time wisely. So let's do another example. Let's take the case of 3. So when is 3 a square? So by the main law, assuming p is not equal to 3, although I guess I said it doesn't matter. The main law is true either way. P minus 1 over 2, 3 minus 1 over 2, p on 3. And 3 minus 1 over 2 is 1, so this is just the product -1 to the p minus 1 over 2, p on 3. And again, when is this equal to 1? That's, again, we just need both symbols, both expressions to be 1 or we need both expressions to be -1. And if we solve each case, this one, P is 1 mod 4. This one, we flipped it around. So now it's just a modular arithmetic calculation that only happens, the only square mod 3 is 1. This makes P 3 mod 4. And then the last option, P has to be 2 mod 3. And so now you just merge the congruences together. Since the mods are relatively prime, we can always glue them together by the Chinese remainder theorem, but it's a concrete example. So you just check out what happens mod 12, and this one is 11 mod 12. And so 3 is a square mod P, exactly when P is 1 or 11 mod 12. And you could, if you wanted to, just rewrite that as plus or minus 1 mod 12. So generally speaking, if the numerator, if I'm allowed to call it the numerator of the Legendre symbol, when I was first learning this, I really didn't like that because they're not fractions, but eventually I was more relaxed about it. Numerator, denominator, top, bottom. In any case, if the numerator has a lot of factors, when you break it up like this, you might have a product of several expressions equal to 1. And so then you have to take more than 2 cases to work things out. But because of the Chinese remainder theorem, you can patch things together and you get things like that. So in general, the general story here is that the expression for A on P being equal to 1, whoops, sorry about that. If you wanted to solve for when is A on P equal to 1, this is a set of P that can be described by congruence conditions. Congruences, usually, or always it could be done mod 4A. Maybe I'll say 4 absolute value of A in case A is negative. So we just saw for when is 3 is square mod P, it's turned by P mod 12. When is 2 is square mod P, it's turned by P mod 8. When is minus 2 is square mod P, P mod 8 if A is minus 2. Sometimes you could reduce this, say just to modulus A alone, but you can always do it as a uniform statement in terms of congruences mod 4A. Are there any questions? You can raise your hand if you have a question or speak up. So great. We can use quadratic reciprocity to determine the primes for which A is a square mod P. And it always turns out to be congruence conditions. If you try to do this for higher powers, describe the primes for when, so maybe I should kind of warning here, that trying to describe the primes for which 2 is a cube mod P, this is definitely not described by congruence conditions. It's a much more complicated thing. If you tried to tabulate the primes P for which 2 is a cube mod P, you would see that it's a much more mysterious set of prime numbers. So something sort of special about working with squares. All right. So the next thing I want to do with quadratic reciprocity, or really these kind of square patterns, is to look at some special cases of Dirichlet's theorem. So we're going to, let me remind you of Dirichlet's theorem. So Dirichlet's theorem says that if you have some integers that are relatively prime, why is this? If A and M have GCD1, there are infinitely many primes that are congruent to A mod M. And when Dirichlet proved this, I mean, many people would say the methods he created to prove this theorem in complete generality was kind of the starting point for analytic number theory. Other people say, no, when Euler did his work 100 years earlier, that was the start of analytic number theory. In any case, what he did was certainly a watershed moment in the development towards analytic number theory. So the general proof of this theorem, it's a kind of a brilliant combination of analysis and algebra using characters on finite abelian groups and infinite series L functions of those characters. But if you take some specific cases, specific congruences, you can prove this result in a much more elementary way. I should say the Dirichlet theorem here also has a quantitative, this is just a qualitative statement. There are infinitely many primes satisfying a congruence condition as long as A and M are relatively prime. There's an additional part that quantifies the proportion of primes that satisfy this condition in terms of some notion of density, but we're just going to take the qualitative statement. There are infinitely many primes satisfying some congruence condition, and so let me show you that we can, in some cases, prove this in a very simple way using the square patterns that we just saw coming out of quadratic reciprocity. So let's do that. So here's a theorem. I'll put them as two statements together when the modulus is 4. I wish I understood why this. Oops. First, we'll do there are infinitely many. Infinitely many primes that are 1 mod 4 and infinitely many primes that are 3 mod 4. So, of course, by silly logic, oh, there are infinitely many primes. One of them has to be infinite. That's not what I have in mind here. Each one separately. There are infinitely many primes that are 1 mod 4 and infinitely many primes that are 3 mod 4. So both sets are infinite. Of course, you're not going to be hunting around for infinitely many primes that are 0 mod 4 or 2 mod 4. There's a reason Dirichlet's theorem has A relatively prime to M. So the two congruences look equivalent to each other. They're just two congruences mod 4, but we'll see in this particular proof that, in fact, the second case is much simpler. So we'll do that one first. So we'll first treat the primes that are 3 mod 4. And the reason I'm going to do that case first is because we can actually just mildly adapt. Both methods of proof will adapt Euclid's proof of the infinitude of primes, but this second case for 3 mod 4 looks very similar to Euclid's proof. The 1 mod 4 case involves a little bit more content to it, and that's where we'll see a square pattern coming in. So what we're going to do with Euclid, he assumes there are finitely many primes and then finds a method to generate a new one. So we'll just say, so let's let P1 through PR be primes that are 3 mod 4, any finite list of primes satisfying that condition. Okay, there certainly are examples. And then what we're going to do with this list of primes is we're going to form a new number. So in Euclid's proof, what do you do with your list of primes to create a new number in that proof? You multiply and add 1. So what we're going to do here is we're going to multiply them together with 4 and subtract 1. So because there are such primes, our list is not empty, so this number is a positive integer. And because the first term has a factor of 4, the whole thing here is odd. And what we're going to do then, and let's observe also that n, if you reduce it mod 4, you can see it's 3 mod 4, and it's a positive integer. And so what that means then, because it's odd, its prime factors are odd, and the prime factors are not all 1 mod 4. Because if they were, then n being the product of its prime factors, since it's positive, would also have to be 1 mod 4. And so thus the number n actually has to have a prime factor that's 3 mod 4. let's say P, such that P is 3 mod 4. And so with this prime, if you look at the nature of this number n, given how it is presented to us, certainly P is not one of the PIs. The PIs don't divide n. And so since P is not equal to any PI, our list of primes that are 3 mod 4, I guess you could say maybe is not complete. So there must be another one. In fact, we just found another one. And so thus there are infinitely many primes that are 3 mod 4. It looks just like Euclid's proof, a linear expression in the product chosen in a careful way. So now we're going to treat the primes that are 1 mod 4. And if you take a look at this argument, so suppose you're trying to come up with a proof that's 1 mod 4. What would you say, well, let's take a list of primes that's 1 mod 4. I can think of examples, 5, 13, 17. So what would you want to use for n? Similar to this thing in red in the box. The negative of n. Minus 4p1p? Oh, you just changed the minus 1 to a plus 1. Sure, right? You take 4 times the product plus 1. The problem, though, and it's a positive integer, and it's 1 mod 4. The problem is you can't really argue that its prime factors cannot all be 3 mod 4, because if they were, a product of numbers that are 3 mod 4 could be 1 mod 4. See, there is a difference between 1 and 3 under multiplication. So this method won't work by switching minus 1 to plus 1 for the primes that are 1 mod 4. So we're going to need to use a different idea. And what we're going to do is we're going to take a nonlinear expression in the product of the primes. So now we're going to treat 1 mod 4. Okay, so what's going to happen in this case? So it'll start off in the same way. Whoops. So we're going to we'll let P1 through PR be primes that are 1 mod 4. And we certainly know some examples. And so then what we're going to do is we're going to define a new number, n. And so this number will be twice the product, all squared plus 1. Okay, so this expression, the new aspect is we're taking a nonlinear expression in the product. It's not just a first-degree expression in the product. And so this number, again, like the previous one, whoops, sorry about that. I guess I can just go back. And so this expression here, this is odd, and this expression is 1 mod 4. And so now what we want to do is argue about the prime factors of n. So let's just let P divide n be a prime factor. Since n is odd, I should have said here, of course, n is bigger than 1, obviously. And necessarily the prime factor is not 2 or any pi. And the thing is that when I say p divides n, so n is 0 mod p, from the definition of n, this expression squared plus 1, that's 0 mod p. And so we can solve minus 1 is this whole thing squared. And so therefore, minus 1 is a square mod p. And p is not equal to 2. and so therefore P is 1 mod 4. So whereas in the previous proof, that n had some prime factor that was 3 mod 4, actually what's happening here is every prime factor of this n will be 1 mod 4. And we already pointed out P is not one of the PIs, so this list of primes that are 1 mod 4 is not the whole list. No finite list of such primes is complete, and so therefore there are infinitely many primes that are 1 mod 4. Okay, so P is 1 mod 4, 3 mod 4. There are infinitely many primes of each type, and you can use this argument in certain other cases. So that ends the proof. And so if you use the rules for the square conditions for when -1 is a square, for when 2 is a square, or for when -2 is a square, those are 3 separate collections of congruence conditions. You can show in the same way that all the options mod 8, infinitely many, all the infinitely many primes P satisfy each, satisfy P could be 1 mod 8 or 3 mod 8 or 5 or 7. Again, not in the stupid sense that, oh, one of them has to be satisfied. But each one of these separately can be, is true for infinitely many primes. And you use these square conditions and a quadratic type of polynomial expression. And now I'm hesitating. For 1 mod 8, I take that back. Yeah, for the non-trivial, for the 3, 5, and 7 mod 8 conditions, you can use these square rules. To show that infinitely primes that are 1 mod 8, you want to go to a higher degree polynomial, even beyond degree 2, but I don't want to get into that here. So in any case, so you can do this in a limited way you can do this for mod 8. You're not going to find an elementary argument like this for the infinitude of primes that are, say, 2 mod 5. There's something in the nature of mathematics that makes this kind of method basically not apply to that case. But Dirichlet handled the general story anyway. But you're not going to use anything like quadratic reciprocity to do something like infinitely many primes that are 2 mod 5. All right. Any questions? No? OK. So let's switch to another topic where square patterns can tell us something. We'll look at some Diophantine equations. So let's consider what's called Mordell's equation. It's really a family of equations. Y squared is x cubed plus a constant, where k is an integer, usually taken not to be 0. And there's a famous theorem of Siegel that such an equation only has finitely many, possibly no, integer solutions. So for each non-zero integer k, this equation, y squared is x cubed plus k, has only finitely many integer solutions. So a famous example that goes back to Fermat, he liked to challenge the British mathematicians, saying he could do various things. Could they do it too? Was the equation y squared is x cubed minus 2. It has integer solutions 3 for x and plus or minus 5 for y, and that's it. Okay? So the general proof of Ziegel's theorem is quite complicated, but some special cases can be handled. Some special cases of no solutions in integers can be handled using these kinds of square patterns coming out of quadratic reciprocity. So let's talk about one of them. We'll use k equal 11. We're going to show that this equation when k equals 11 has no integer solutions. It's going to be an argument by contradiction. And so that's why when there are solutions, this method I'm going to show you doesn't really quite work. Whoops. The equation y squared is x cubed plus 11 has no, let's fix that, has no integer solutions. So I should perhaps make a remark. It does have rational solutions, such as, for example, minus 7/4 and 19/8. In fact, it has infinitely many rational solutions. So the emphasis here, again, as in Ziegel's theorem, is about integer solutions, and the statement is there are no integer solutions. If your equation, polynomial equation, is not homogeneous, there could be a huge difference between the integer solutions and the rational solutions because you can't scale through the equation to turn rational solutions into integer ones. So this is not a homogeneous equation at all. All right, so how are we going to show that this equation has no integer solutions? So we're going to assume that there is one, and we're going to get a contradiction. So let's assume xy is a solution. What we're going to do, the first step is to show that x is 1 mod 4, and then we're going to proceed from there. It's not obvious from the equation why x should be 1 mod 4, but what we're going to do is we're just going to make a table. Make a table of all the possible values for y and y squared, and x cubed plus 11 mod 4. And we'll see what we get. So y could be, whoops, sorry about that. Y could be 0, 1, 2, or 3. And when you square even numbers, mod 4, square to 0. Odd numbers square to 1. And x could be 0, 1, 2, or 3. If you cube them and add 11, 11 is 3 mod 4. So I get 3. 1 plus 3 is 0. 2 cubed mod 4 is 0. That's 3 again. 3 is minus 1. 3 cubed is minus 1. 3 minus 1 is 2. Now, if you look at these, you see that the only matching values are the 0 values. And so for these to be equal in the integers, necessarily x has to be 1 mod 4. And y has to be 0 or 2, so y also has to be even. But for us, the main point is that x has to be 1 mod 4. So we're going to use that next. So if there's a solution, x has to be 1 mod 4. How are we going to use that? Well, what we're going to do is a clever, unmotivated adjustment to the equation. If y squared is x cubed plus 11, then if I add 16 to both sides, we change the 11 into a 27. And the nice thing about 27, it's a perfect cube. And we know how to factor a sum of 2 cubes. It's x plus 3 times x squared minus 3x plus 9. So we're going to stare at the second factor in this equation and try to do something with it. So the first thing to observe even though it has a minus sign in the middle, it is positive, since if you just complete the square, x minus 3 squared plus, I guess you have to add 9 minus 9, anyway, 27 fourths. Is that right? 9 plus 27 is 36 fourths is 9. Yeah. So it's a sum of two positive things. This is definitely positive. And if x, so the second factor is a positive integer no matter what x is, even if x were negative. And since x is 1 mod 4, this expression x squared minus 3x plus 9, if you look at it mod 4, it's going to be 1 minus 3 plus 9. 10 minus 3 is 7, mod 4 is 3. This is going to be 3 mod 4. So the second expression is 3 mod 4. So what that means then is that the second expression, x squared minus 3x plus 9, it's a positive integer, and it's 3 mod 4. Now, what did we learn earlier about positive integers that are 3 mod 4? In terms of their prime factors? Anything? What? There's got to be at least one that's 3 mod 4. Not that they all are, but it has to have at least one. So it has a prime factor. That's 3 mod 4. Great. So now we're going to take a look at the left side. Y squared plus 16 is this product up at the top, and the second factor has a prime factor that is p is 3 mod 4. So anyway, this left-hand side is definitely 0 mod p. P divides the right side, so p divides the left side. And so you can say minus 16 is y squared. Minus 16 is a square mod p. And p is odd, since p is 3 mod 4. If minus 16 is a square, we can divide through by 16, absorb that into the square factor, and get that minus 1 is a square. But of course, 0? Minus 1 is a square. Is that not square enough for you? It's a square. So, whoops. Congruent to, I thought if I stopped it would square it out. Anyway, minus 1 is a square. So that implies, this thing is really getting on my nerves. That implies that p is 1 mod 4. Nope. Contradiction. P was 3 mod 4, now it's 1 mod 4. So that's a contradiction, and therefore our proof is over. There are infinitely many people. The worst thing I could have said. This equation has no integer solutions. Again, it has rational solutions, but that's a different story. And maybe in the course on elliptic curves, somebody will say something about that, the rational solutions to that equation. Maybe not. So I want to emphasize, when you try to prove, I mean, for those who've proved some Diophantine equations have no integer solutions, what kind of methods have you used? If I gave you some equation, I want to show it has no integer solutions. Anybody remember ever doing something like that, saying something like that? What? You could factor, yeah. Anything else? What? Descent, okay. Height functions, getting a little bit more advanced than I wanted to. Yeah, reduction. I should just wait around until somebody says some. Reduction mod m, right? The simplest method that you often see being used over and over in elementary cases is just using reduction mod m, right? So maybe I should make a remark here. So you can't, we did use reduction mod 4 here, but that was combined with other things. Okay, so let me just emphasize, you can't prove that some Mordell equation has no integer solutions just by reduction mod m, hoping that maybe there's some, for a particular Mordell equation with no integer solutions, maybe there's a magical modulus modulo which there are no solutions mod m, and then I'd be done. But you can't do that because actually it turns out, even though Mordell equations may sometimes, like here, have no integer solutions, the congruence y squared is congruent to x cubed plus k. Mod m always has a solution for each m. Okay, y squared is x cubed plus 11 actually has a solution mod m for every m. So if you want to see some arguments leading up to that, if you go to Math Stack Exchange, question number 875983. And Math Overflow question 134352. Okay, some discussion around that topic. So anyway, okay.
Is that has a solution like integer solution or just?
Yes. That's what. Oh, when I talk about solutions, I'm just talking about integer solutions. Yes. When I reduce mod m, there's a solution mod m, an ordinary z mod m. No, I'm not talking about higher things or anything like that. Yeah. Okay. So you can use modular arithmetic like we just did, but you have to use other things. Like once we did something mod 4, we then went back up into the integers, used prime factorization and other stuff, and used the rule for when -1 is a square. Well, mod p for the p that came up. In any case, it's not purely an argument mod m for one m. It's not the idea of just showing no solutions mod m for some m. Yes, question?
On our last proof, is there any part of this argument that specifically is breaking for rationals other than because we could take inverses mod 4, I mean, I guess your solution.
Notice my rational solution example has denominators 4 and 8.
But
So,
would our solution generalize to odd denominators?
So, yeah, if you had a rational solution, well, I mean, here when I was doing the right side is an x squared minus 3x plus 9 is a positive integer that's 3 mod 4, so it has a prime factor that's 3 mod 4. If x was merely rational, it's not clear what you would, if you have a rational number, odd numerator and denominator that's 3 mod 4, I guess either the numerator or the denominator has to be 3 mod 4. But, so it looks like it would get complicated. In any case, there are actually rational solutions, so we're using, but maybe. Okay. Any questions? No? All right. So, so the last thing I want to discuss today, another Diophantine equation, is asking about, so here's the basic question. If we have an integer d that's not a square, we could ask, what are the prime values of x squared minus dy squared as x and y run over the integers? Okay. So questions like this go all the way back to work of Fermat. So for example, Famously, a prime, if we take d equal to -1, to say a prime is a sum of two squares when d is -1 in Z, that happens if and only if P is 1 mod 4, or as another example, a prime is x squared minus 2y squared in Z for integers x and y, if and only if it's 1 or 7 mod 8. You look at the right side, and that reminds you of the rule for when -1 is a square, d is -1. And in the second example, that's the rule. 1 or 7 mod 8 is the rule for when 2 is a square mod p, and we see the number 2 is, well, the equation on the left side involves d equal to 2. So there's some connection. So there's definitely a link between P having this expression and D being a square mod P. When D is -1, I'm saying P being a sum of two squares is related to -1 being a square mod P. When D is 2, P being x squared minus 2y squared is related to 2 being a square mod P. So one direction we can show without a problem in all cases. So let's do that one. So if P has this form, then D is a square, no matter what, even with P equal to 2. Well, of course, everything is a square mod 2, so it's kind of a silly statement there. But in any event, anytime a prime has this expression in this quadratic formula, quadratic form, literally, in x and y, D has to be a square mod P, period. So let's see, proof. When P is x squared minus dy squared, in the integers, meaning x and y are integers, P does not divide y. Because if P did divide y, the left side is divisible by P, and then the second term on the right is divisible by P. So then it has to divide the other term, x, but then on the right side, x squared minus dy squared is divisible by P squared. And that's a contradiction since the left side is just P alone to the first power. So P cannot divide y. So now we're just going to reduce mod P. 0 is x squared minus dy squared. So x squared is congruent to dy squared. Now, because P doesn't divide y, not 0, and so we can divide by y squared. Now when you divide by y squared, the left side, x, y inverse all squared, is congruent to D. So in other words, D is a square. And we'll end the proof with another square. So there we go. If P has a chance to be of this form, then D must be a square mod P. In fact, the only thing we used about the left side of the equation, it didn't have to be P. It could have been any multiple of P that was divisible by P only once, because I needed the left side at least not to be divisible by P 2 times. But in any case, we'll keep it simple. Just if P is going to be x squared minus dy squared, D must be a square mod P. And so the big question now is the converse direction. Okay, what about the converse? If we know that D is a square mod P, D is a prime, P is a prime, D is an integer that's not a perfect square in Z. If D is a square mod P, does P have to have this form for some x and y in the integers? The answer is no. It doesn't have to happen. No. Let me show you two examples. So, for instance, one example could be, where am I here? I'm looking at my notes. D is a square, so 10 is a square mod 3, 10 is 1 mod 3, but 3 is not x squared minus 10 y squared. Since if it were true, I would say 3 is not equal to a square mod 5. If you reduce both sides mod 5, if 3 were x squared minus 10y squared, reduce mod 5, 3 would be x squared mod 5, but 3 is not a square mod 5. And another example is that I want to use 3 is a square mod 11, but, right, can anybody see why 3 is a square mod 11? Give me an actual 25, right? 3 is 5 squared mod 11, but 11 is not x squared minus 3y squared mod z. Why is that? That's because 11 is not a square mod 3. So, yeah, so it doesn't always work, but it turns out that if you add a certain extra condition that we'll discuss starting in lecture 2, we'll see that you can make the converse work under suitable circumstances. Okay, and so that's where I'll stop today. Thanks.